Welcome to the Composing with Sound lecture for week 3 entitled Sound Shapes. In this lecture, we're going to talk a little bit about describing sound shapes. We're going to discuss envelopes and complex sound morphologies. And finally, we're going to talk a little bit about the relationship between gesture and texture. When it comes to describing sound shapes, we can characterize most musical instrument sounds in terms of two characteristics: the excitation and the resonance. The excitation is the action that gets the sound going, and the resonance are the properties of the sounding object that sustain and amplify the excitation. I'm going to give a quick demonstration in a minute with a tuning fork and a whistle. And the difference between those two is in terms of both the excitation and the resonance. So in terms of excitation, we can divide the mode of excitation into two categories. The first is impulsive excitation, like striking a percussion instrument or plucking a guitar string, and sustained excitation, like the blowing associated with a wind instrument or the bowing associated with a string instrument. So in these two examples, you can see that in the case of the triangle, the energy associated with the excitation lasts only a very short fragment of a second, but the resonance of the metal rings on for quite some time, and it has a characteristic overtone series that, well, in the case of this cheap triangle, doesn't have much of a pitch. Whereas with the penny whistle, the excitation lasts for the entire duration of my breath, and the instrument only makes sound while the excitation continues. So the whistle requires sustained excitation. And in the case of the whistle, the resonance is caused by the air within the tube oscillating backwards and forwards from the open end to the closed end. Okay, so we've started to characterize the typical sound types that we get with musical instruments. And the English New Zealand composer Dennis Smalley introduced the concept of spectromorphology. So this is a rather fancy term, but we can break it down into its two component parts. Spectro stands for spectrum or frequency spectrum, and morphology is just a fancy word for shape. So we're talking here about the shape of the frequency spectrum of an instrument or of a sound as it evolves over time. So Dennis Smalley linked the excitation and resonance of instrumental sounds to the change in spectrum that occurs during the life of a single note. He called this the energy motion trajectory. So in the videos that I just showed of me striking the triangle or blowing in the whistle, if you close your eyes and imagine the cause of those sounds, you can imagine a kind of physical striking going on, the motion of the beater against the triangle, or in the case of the whistle, the motion of the air, my breath, entering into the instrument. So there's this kind of imaginative trajectory going on when we listen to a sound. So in terms of acoustic instruments, typically the more energy that goes into the excitation, the brighter and louder, and sometimes the more chaotic the sound that is produced. So for example, if I overblow the whistle, I get a shrill, chaotic sound caused by the turbulent airflow in the whistle. So Smalley identified three basic kinds of sound shape, or envelope. So envelope is a word that is used to describe both the change in the amplitude and the change in the spectrum. So we can talk about the amplitude envelope, the loudness envelope, and the spectral envelope. And he identified three basic kinds. There's sounds that are an attack alone, typically from a damped percussion instrument. For example, this finger click, which which has no resonance. The attack decay sound shape, in which the sound starts decaying as soon as the attack portion is over. For example, my triangle, a bell, or a violin pizzicato, a plucked string. And then the third type is the graduated continuant, where we have continuous excitation. And as we change the energy in the excitation, whether that's bowing a string or breathing into a whistle, the continuant portion of the sound changes during the life of the sound. So in this musical example from Dennis Smalley's 2000 composition Base Metals, you can hear the composer exploring what happens when we defy the listener's expectations about natural sound shapes. So this is really taking spectromorphology and applying it as a compositional design. Let's just hear a little piece from the beginning of Base Metals. So you can hear in this example that we get that typical impulsive excitation of a metallic sounding inharmonic timbre, and instead of it dying away as a attack release classic sort of expectation that we might have of striking a metal resonant object, uh, unexpectedly the partials rise back up again and take on a life of their own and evolve and develop throughout this minute or so that we heard. And this is one of the central ideas behind this compositional approach. So, in the early days of computer music research, it was found through digital spectrum analysis of typical instruments that their sounds could be characterized as a series of harmonics or partials in the way that we described last week. And Mora and Gray, in their 1979 articles, Lexicon of Analyzed Tones, which were published in the early editions of the Computer Music Journal, analyzed a trumpet and a violin and various other instrument sounds. So we're looking here at a diagram that comes from that article, so it's rather poor quality in terms of its reproduction. But this three-dimensional graph shows time in seconds across from left to right, going from 0.0, 0.1, 0.2, 0.3 of a second. So this note lasted for about 0.4 of a second. Going front to back in the diagram, we get the individual harmonics, harmonic number it's shown. So the first, second, third, fourth, fifth, sixth, seventh, up to 16 harmonics. And the vertical axis shows the amplitude in decibels. So harmonic number one well, actually, it's a little bit difficult to read on here, but it looks to me as though harmonic number three, perhaps, or harmonic number four is the highest amplitude in this particular recording of a violin tone. And you can see that the higher harmonics are much lower in level, and they die away more rapidly than the lower harmonics, which sustain for quite some time. In fact, the fundamental, which you can kind of see is perhaps the third highest in amplitude, is definitely the longest in terms of the time that it lasts for. So, this approach to analysis of sounds in terms of the harmonic components, which in fact goes right back to a research that was done at the end of the 19th century by a guy called Helmholtz. It suggests that sounds could be reproduced by combining individual sine wave oscillators whose amplitudes were mapped onto the amplitudes that are shown in the analysis diagram here. And that method of synthesis was called additive synthesis, and it was one of the first techniques that was developed in computer music. So here is a schematic diagram which shows how a typical additive synthesis patch might be comprised. Now you'll see schematic diagrams like this in the literature, in books about sound synthesis. And on the right we see the individual modules that make up a typical synthesizer. So the first is an oscillator, in this case a sine wave oscillator. You can see that characteristic sine wave shape there. The next down, the triangle shape stands for an amplifier. You'll notice the letters VCO and VCA stand for voltage controlled oscillator and voltage controlled amplifier. So the frequency of the oscillator in an analog synthesizer can be controlled by a control voltage, and the gain of an amplifier can be controlled by a control voltage. Now, in the case of digital synthesis, these would be called digitally controlled oscillators. The third symbol is a filter, in this case showing a low-pass filter. The next symbol is for an envelope generator. Now this object produces a control message which will be used to control the amplitude or the gain of an amplifier, or perhaps the cutoff frequency of a filter. And the Greek letter sigma in the bottom right is for a mixer, which is a module that adds together the signals from the various other modules. So we can see in the diagram in the middle, we have 1, 2, 3, 4, 5 repeated sets of the three objects, the oscillator feeding into an amplifier and the gain of the amplifier being controlled by an envelope generator. And so with this system, we can reproduce, for example, the first 5 harmonics if we were able to simulate the envelope shape shown of the first harmonics in this diagram. So I'll show you a quick demonstration of a max patch which basically implements this design for additive synthesis. Here is the cycle object, which is the sine wave oscillator. Here is the multiply object, which is acting as an amplifier, and the combination of the function object and the line object function as an envelope generator. And when these patch chords enter one inlet of this addition object, they're basically being summed together or mixed together. In this version of the patch, I've used the new multi-channel objects that are just new in Max 8. And there's something that I haven't played with very much, so I've taken this opportunity to build the same patch. And I've added some reverberation, and I've added some more life to the sound in the way that Dennis Morley has in base metals. Okay, so there's a another video on this week's section on UTS Online, which explores the idea of amplitude, and it uses this diagram from the Cipriani and Giri text, which tries to explain how an amplitude envelope is applied to a signal. So in the research that Gray and Mora did, they discovered that they could simplify real acoustic amplitude envelopes down to linear segments. We call these piecewise linear envelopes. And they found that by reducing one of these complex envelopes down to just 4 linear components, they could produce a convincing reproduction of the sound without much distortion. As a result of this early work, a standard approach to the design of the envelope called an ADSR envelope generator was widely adopted. So ADSR stands for attack, decay, sustain, and release. And we can see here in this envelope, this is the attack portion of the envelope, decay portion of the envelope. So most acoustic instruments rise up and then decay rapidly, and then there's a sustained portion and then a release. And you could see in my max patch that the envelopes that I'd created there were modeled on this idea of piecewise linear envelopes, and in that case they were produced with the function object. So what happens in our additive synthesis patch is that we start with a sine wave oscillator, which produces a continuous tone at a fixed amplitude, and we multiply that amplitude by the level in the envelope, and the result is a sound that rises up, falls down, sustains, and ultimately decays or releases. So piecewise linear envelopes, just to restate these details, ADSR stands for attack, decay, sustain, release, but actually the parameters are slightly different to each other. The attack time is the time taken for the signal to rise to its highest level. The decay time is the time taken for the signal to fall to the sustain level after the original attack. The sustain level is the level maintained during the sustained period. For non-sustaining envelopes, for example, a piano note, this is the time taken before the release occurs. And the release time is the time taken for the signal to be attenuated after the envelope is released. So this is the time taken to decay from the sustain portion down to silence. And finally, there's really 2 modes of envelope control. An envelope may either sustain indefinitely at the sustain level until it's released. So this would be typical of, say, a bowed instrument where you can continue bowing endlessly. Or alternatively, it will play through each stage of the envelope up to the end of the sustain, and then the release will occur. So a plucked string, for example, is not a sustaining sound. The release occurs after the sustain period has completed. So there are a number of different ways of achieving envelopes in Max. The first patch here shows the use of a line object. The message object here says start at 0 and then rise up to a maximum amplitude of 1 over 50 milliseconds, fall away to an amplitude of 0.8 over 30 milliseconds, retain that level of 0.8 for a further 300 milliseconds, and then fall to a level of 0 over 300 milliseconds. So the line object understands these pairs which say target level over a given amount of time, target level given amount of time. So you get these pairs of values. The second way of generating an envelope, which I've done in my example patch, is the function object. Function object is a great object. It's kind of interactive. We can draw in envelopes, and we can either make it sustaining or non-sustaining, and a bang sends out the pairs of values, the target level and time, which are understood by the line object. So those pairs of values come out of the second outlet of the function object. And the final object that I'm showing here is the ADSR object. So this produces an audio signal which is used to drive the multiply object directly. And here we enter the attack time, the decay time, the sustain level, and the release time. So you can see here an attack time of 50 milliseconds, a release time of 30 milliseconds, a sustain level of 0.8, and a release time of 300 milliseconds. One small thing to note here is that the ADSR object, rather than responding to a bang, responds to a 1 to start and a 0 to trigger the release. Okay, now I'm going to introduce the concept of subtractive synthesis. A simpler method of creating complex waveforms is to start with a complex waveform rich in harmonics, such as a sawtooth wave, and then filter it down to remove some of the frequency content. It's common for acoustic instruments to start with many harmonics and then for the upper harmonics to reduce in level over the life of the note. Therefore, an envelope generator can be used not only for the amplitude, but also for the cutoff frequency of a low-pass filter. This patch demonstrates a design that uses a function object to control the amplitude envelope, the frequency cutoff, and some detuning of the pitch over the note, which is typical of acoustic instruments such as a piano, which start sharp and then fall down to their natural pitch. Okay, so now I'm going to introduce some ideas from Dennis Smalley's work on spectromorphology. The sounds considered so far could have been produced with acoustic instruments. These sounds are linked to the physical gestures that help to create them. We've described these gestures in terms of excitation. Smalley uses the term source bonding to describe the link between what we hear in the sound, its intrinsic features, and the imagined external causes that we might speculate about. This link is part of what we hear and may become part of the compositional design, as heard in Dennis Smalley's piece, Base Metals. So another way of thinking about source bonding is to do with the language that we use to describe sounds. So I could say, for example, I heard a knock at the door. So here I'm describing the source, the door, and the gesture that caused that sound to happen. Smalley calls this a source-cause description. So one further extension from this idea of spectromorphology is to think through the relationship between gestures, so the knock at the door, and what we might think of as textures that belong to longer sustained sounds. And in Smalley's piece, Base Metals, he's playing with this link between gestural causes of sounds and then turning those into evolving textures, like we might get with a string section in an orchestra. So I'm going to leave you with a bit of a mental exercise. Consider the envelope below. How might this sound if this envelope was applied to amplitude, to the spectrum or the cutoff frequency of a low-pass filter, to pitch? For each of the parameters above, how might this sound if the envelope duration was 100 milliseconds long, so a tenth of a second, 1,000 milliseconds, a whole second, or 10 seconds? Imagine the results of those different types of operations on the sound and think of those as perhaps the starting point for a moment in a composition. So we set out to describe sound shapes, to introduce envelopes, to discuss complex morphologies, and finally to discuss this idea of gesture and texture. I'm hoping that you will have some questions for me in the tutorial. There are a set of relevant references that I've referred to in the lecture, and that concludes the lecture. Thanks for listening.